not everybody is there. Let me just remind you what we did last time, and today we'll start to discuss the construction of an interacting quantum field theory using the method of a functional integral. So remember, what we did last time, we extended to a quantum field, a very simple quantum field that was a free field, non-interacting scalar field describing non-interacting particle with no spin. We extended the recipe of path integral to try to quantize this field. So we had a field phi of x, which is real, no in space-time, no spin. X denotes, remember, time and space, and I am using the metric with minus plus 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 signature squared. Okay. The action for this field is the integral over space-time of minus 1/2 d mu phi minus m squared over 2 phi squared. This is the action for a free field. So they are just quadratic. And remember, if we are interested in working in Euclidean space-time, this becomes integral d dx 1/2 d mu phi plus m squared over 2 phi squared. This is Minkowski and Euclidean space-time means that ds squared equal d tau squared plus d x squared. Okay? And we could define a functional integral simply by d phi exponential I over h bar s of phi in the Minkowski space-time or in the Euclidean space-time exponential of minus 1 over h bar se of phi. Okay? So, now the rules of functional quantization implies that, for instance, if you are interested in computing in Minkowski space the vacuum expectation value of a product of two fields operator at 2 points x1 and x2, this is given simply by computing this object integral d phi exponential of I over h bar s of phi of x1 phi of x2 divided by d phi exponential of I over h bar s of phi and with no phi. Okay? And since this is a Gaussian measure, this is simply given by the inverse of this operator. Okay, so this implies that this is given by the matrix element, if you want, between the point x1 and the point x2 of the operator And in this case, this will be, there is an I, there is an h bar, so this will be h bar minus h bar I times this operator minus, and if you lambda squared minus m squared. Yes. Okay. And we have seen that its Fourier transform, so this will be noted as the propagator, g of x1, x2, and we have seen that it's simpler to compute it in its Fourier transform. And its Fourier transform, g hat of some momentum, 4 momentum k, is simply minus I over k squared plus m squared, and with the Feynman recipe. So this is just the Feynman propagator. And remember, if x is a momentum, k is a frequency and a space momentum, and but this is in fact a covariant vector where the position is a contravariant vector. So with my notation, k squared equal minus omega squared plus k squared. Okay. So this function is called the propagator, Feynman propagator, or the 2-point Green function, because it corresponds to this matrix element between the vacuum of this time-ordered product of operator. And of course, omega naught, this is the vacuum, ground state of the free field system. Okay? And we have seen also that you can derive that by starting from phi of x1, phi of x2 is the expectation value of this in Euclidean space. And making a Wick rotation. And in Euclidean space, this function is simply g of x1, so x1, x2 equal the matrix element between 2 points x1 and x2 of h bar over minus the Laplacian plus m squared in Euclidean space. Okay, so this Laplacian here is simply d squared over dx mu squared, sum from mu equal 1 to d, because we are in Euclidean, where this Laplacian here, remember, you have to change the I'm sorry, why is there a square? This is not a Laplacian square. I'm completely stupid. This was the front. This is the, and there is a minus, I think. Okay. No. Okay. Well, here, this is a Laplacian in Minkowski space. Okay. Now, Good. And its Fourier transform is g hat of k equals simply h bar over k squared plus m squared, where k now is, of course, just a product of the momentum. So remember, x is tau x, and k is k naught k, and k squared is k naught squared plus k squared. So that's just the usual scalar product in Euclidean space. Okay? So we have seen that this function, that it is so the Wick rotated Feynman propagator G is a function of, in fact, of x1 minus x2. And we have seen that it has a property at short distance. So when x1 goes to x2, it behaves like x1 minus x2 to the power 2 minus the dimension of space-time. Space-time dimension. So it diverges at short distance. And that's something that doesn't happen in quantum mechanics. And it diverges as long as the dimension of space-time is larger or equal to 2. And the higher the dimension, the stronger the divergence. So this kind of divergence are called ultraviolet divergences. Ultraviolet because short distance means high frequency, so high energies. And this is a very important and specific feature of quantum field theory. Important feature of QFT. And we'll see how to treat and to deal with this feature in perturbation theory in the next lecture. This is the purpose of renormalization theory. Okay. So now, of course, since the measure is Gaussian, we have also seen another feature, which is that we can apply Wick theorem. Wick theorem becomes just the properties of Gaussian integrals. Okay? And it means simply that if you want to compute, for instance, the vacuum expectation value of a time-ordered product of 4 operators, fields operator, phi of x1, phi of x2, phi of x3, phi of x4 in the vacuum, then we simply have to write them as a sum over pairings of the products of the corresponding propagator, namely OT of phi of x1, phi of x2, this is a pairing, times T of phi of x3, phi of x4, plus of this type. Okay? And for this particular case where we have n equal 4 point function or green function, we simply have 3 pairings because we can represent this by stating that this 4-point function, when I have a point 1, a point 2, a point 3, and a point 4, and this represents the full green function, this blob, this is in fact equal just to this propagator 1, 2, 3, 4, plus this propagator, 1, 3, 2, 4, plus this product of propagator, 1, 2, 3, 4. Okay? And that's it. That's exactly the same Wick theorem than the one you have been discussing in the QFT1 course. Simply the proof here is different. We are not dealing with operator defined as operator acting on a Fock space. We are not using the fact that this operator can be expressed in terms of creation and annihilation operators, the modes of the fields. We are not using the commutation relation of the creation and annihilation operator to show the Wick theorem. We are just using the fact that in the functional integral formalism, these objects are given by Gaussian integrals. And we are using the properties of Gaussian integrals. But the final result is the same. It's just two different derivations of the same results because we are constructing these results, the green function, by two apparently seemingly completely different mathematical methods. Okay. Good. So, now, perhaps one last remark before going to perturbation theory. In the path integral formalism, in the functional integral formalism, we are doing with fields. So we are constructing directly the field operators of theory out of a functional integral over classical field configuration. So we are considering fields phi. Up to now, we have not discussed at all particles. Where are the particles? Well, remember, the particles are in fact a single particle in this theory is just the first excited state above the vacuum of the full Hamiltonian of our quantum field. So a particle, a single particle state, a single particle state that you can write K in the notation with, of course, K squared is characterized by, in fact, by an energy, by a momentum such that E squared equal K squared plus M squared. This is just the first excitation above the vacuum state, omega, 0 of our theory. So, how do you see that the first excitation above the vacuum state of the theory we have constructed by this path integral is a particle? Well, in fact, we see this because the propagator, the two-point function, is the same than the particle, the two-point function that has been constructed by the canonical quantization method. So the particle is inside the propagator. And I will explain that later. I don't know if you have seen the Chelon-Lehmann representation theorem. Okay. So I will briefly explain later on, because that's very important, that in fact there is a theorem called the Chelon-Lehmann representation. I will not state what it is at that point. We said basically that the spectrum of the theory of state can be extracted out of the two-point function. well, some information, of course. Not all information, but information about the spectrum of the theory can be extracted out of the two-point function. And in fact, you can see that when you look at the two-point function, remember, the two-point function in momentum states is 1 over omega squared, that's minus omega squared plus k squared plus m squared. Well, plus minus is I epsilon plus with a factor minus I. So you see that in the k squared equal k squared minus omega squared complex plane, if you consider that k is a complex variable, this has a pole at k squared equal minus m squared. And omega is more or less the energy. K is a momentum and omega is an energy. So it means that there is a pole at the states of energy. Something happens when the energy of the states is E, of your quantum state. You compute some quantum state and you see how it propagates, whatever it is. It can be a very complicated quantum state. Something happens when the energy of this state is mass, is equal to m. So the fact that there is a pole means that there is a resonance with a physical state. And I will explain that later. Phenomenon and resonance is something that you know very well, even in classical physics. You have a system with some modes, you excite them in some way, and if you excite them at the right frequency, then the systems gets excited. Okay? And then, of course, the fact that this happens at energy m, and that you have therefore energy, this relation, the pole is at E squared equal k squared plus m squared in general, means that this is a relativistic state invariant, so its momentum and E are related by just the well-known relativistic relation between the relativistic momentum and the relativistic energy. So this physical state is a particle of mass m. Okay, that's just word at that moment, but I will explain that later. So something which was almost obvious, but you have to keep in mind. In my original formulation, m squared was a parameter of the Lagrangian density. Okay, so I defined a quantum theory out of a classical theory whose action, which is the integral of a Lagrangian density, depends on phi of the derivative of phi, and one of the parameters, I call it m squared. Okay. It turns out that this parameter is equal to the mass of the particle of the theory. So it was a good idea to call it m. But this could not have been the case. I could have decided my parameter was m squared over 4 or something different. Then the relation, of course, it would have been a trivial difference. But in general, if you have a theory defined whose Lagrangian depends on some parameter, if it has as lowest excitation a particle state, the relation between the mass of this particle state and the original parameter of the Lagrangian may be more complicated. And that will be very important when discussing renormalization. Okay? So keep in mind that m was denoted mass because it was the mass of the particle, but that's only true, in fact, that's because we are in a free theory. Okay? That's a property of the free theory, because there are no interaction. Okay. Okay, so now, once we have understood that, it was some long reminders, but I think that's important. Of course, we are interested in constructing an interacting theory. And the simplest example of an interacting theory involving a scalar field is a well-known, what's called 5-4 theory. And this 5-4 theory is described by the following Lagrangian. We had to the, well, let me write it in the Euclidean case first. We had to the action of the free theory an interaction term, nonlinear, involving the 4 powers of the, of course this is, the phi squared. We had a nonlinear, well, non-quadratic if you want, quadratic, local term. It's local because this means simply proportional to phi 4 of x. So we take the product of 4 fields at the same point. This is a product of 2 fields at the same point. This is a product of 4 fields at the same point. Okay? So this is the interaction term. G is denoted the coupling constant, because it measures the strength of the interaction, the strength of the nonlinearity. Yes?
I have a question about the discussion of mass.
Yes.
So do you define the physical mass of the theory as the location of the pole of the propagator?
Yeah, it turns out that the fact, yes, it turns out that the fact that there is a pole means that there is a physical state at that energy. So that's how I define the physical mass. That's a mass you measure when you are making an experiment and you observe a particle, and you. So that's the mass of this particular state. Or if you prefer, the energy at rest of this particular state, when it is at rest in your lab frame. Okay? Some other question on that point? I will come back to that later anyway, in 1 or 2 lectures. Okay, so G is called the coupling constant, and this funny factor here of 1 over factorial 4, which is 24, is in fact for convenience. It's just a normalization, but it turns out that it's quite natural to normalize the interaction by 1 over factorial 4. You will see that later. Okay? And that's factorial of 4 because there is a power 4 here. Okay. So this coupling constant will be taken to be, of course, to be positive, because if G is not positive, this term in the Hamiltonian will be unbounded from below. So we want an Hamiltonian which is bounded from below. A classical Hamiltonian. And also, one small remarks, if G is positive, we may take m squared to be positive or negative. Because if m squared is positive, we have a potential V equal m squared over 2 phi squared plus G over factorial 4 phi 4 that has this shape. This is a potential for the field. While if it is negative, we have something like that with 2 minima. So this is if m squared is positive. This is if m squared is negative. But still the potential is bounded from below. Okay. So that's important, in fact, because you have met such functional, action in the in the statistical mechanical course, where this has exactly the same form as something called the Landau-Ginzburg-Wilson-Hamiltonian, describing the mean field theory of some statistical spin system. So there is a connection between what I'm doing here and statistical mechanics. And also, if phi is a bit more complicated with more than one component, this is the action that describes the X field in the standard model. So it's just not a theory that we study for, because it's simple. This model has a physical application, both in statistical mechanics, in high energy physics. Okay. So now, in this interacting theory, of course, then if we, I wrote it in the Euclidean, and in real time formalism, the action will be integral d dx, and again, that's minus 1/2 d phi squared minus m squared over 2 phi squared minus g over factorial 4 phi 4. Okay? Good. So, I think you started to study how to study this theory using the canonical formalism. And the trick to study this interacting theory is to use perturbation theory. So consider that G is small and expand in powers of the coupling constant, the quantity we are interested in. Okay? And we'll see that, in fact, since the propagator is the same, when constructing this perturbation expansion using functional integral, we'll get exactly the same rule of calculation than the one you started to study in quantum field theory, one course. No surprise. But simply, functional integrals are a different way to derive them and to manipulate the objects. And for many calculation and many physical reasoning, they are very convenient. So let's see what we get. So now, in the interaction theory, we are interested in computing green functions, as in the original free theory. So we are interested, for instance, in computing the expectation value in the vacuum of the time-ordered products of fields operator at n different points. Okay, so the endpoint green function in the interacting theory is given by the expectation value between the vacuum of the theory of the time-ordered products of phi operator at point x1, xn. Okay? In space-time. But now, of course, the vacuum omega of the interacting theory is different from the vacuum of the free theory. So it's a different object. The field operator themselves, they may be different operators. It depends how we define them. You have first to construct the Fock space of the interacting theory, construct the vacuum state, construct the other states, so they may be different. The beauty of the functional integral formalism is that, well, the rule, the path integral rule apply as well to an interacting theory as for the free theory. So the rule is that this object, this green function, will always be given as the ratio of a functional integral with the action for the interacting theory, this one, times phi of x1, phi of xn. So I integrate over functions over space-time with this phase factor times the products of those value of this field configuration at the point in space-time x1, xn. And of course, I have to normalize by dividing by d phi exponential I over h bar s of phi. So that's a very formal definition, but we have to compute this object. If we know how to compute this object, we are done. We have all the green function of the theory. And I think Freddy Cacciazzo mentioned that once you have the green function of the theory, you can reconstruct the diffusion amplitudes of the theory, namely the quantities that interest you in high energy physics if you are doing experiments, because you cannot, in general, measure a green function. You cannot say compute correlation, but you can send particles in a collider and see what comes out. Good. So I will denote, also for simplicity, I will denote this phi of x1, phi of xn as in the Euclidean framework. So, since the rule of calculation will be almost the same in the Euclidean framework, I will use generally this notation where this bracket of products of phi means that I'm evaluating a functional integral, the expectation value of this with some weight, and this corresponds to this in the real-time setting. Okay? So, now, the idea of doing perturbation theory is exactly the same than what you did in QFT1. But in QFT1, you had an evolution operator written as exponential of some interaction, some Hamiltonian. That was the sum of a free Hamiltonian and an interaction Hamiltonian. Here we are evaluating a functional integral where the action is a sum of a free action, the first two terms, and an interaction term. You see. So the idea is very simple. We simply that this term we write exponential of I over h bar s of phi. We write it as exponential of I over h bar s0 of phi, where s0 of phi is the free field action. I don't rewrite it. This is just the action here, times exponential of I over h bar g over factorial 4 integral over space-time of phi 4 of x. Okay, so instead of expanding an exponential of an Hamiltonian, of an operator, I'm expanding the exponential of an action. but that's exactly the same idea. And then, of course, this last term, we expand it in power of g. So we write the exponential as a sum from k equal 0 to infinity of 1 over factorial k I over h bar g divided by factorial 4 to the power k times this integral. So now this integral becomes a multiple integral over k different points of the products of those operator phi 4 of x1, phi 4 of xk. Okay? And I can do this expansion. So I use this expansion both in the numerator and the of the formula for phi of x1, phi of xn. Okay? Yes?
Should there be a minus sign in the exponential, even minus ig?
You are...
Or is this...
No? Why do you expect a minus? Oh, yes. No, you are right. You are right. You are perfectly right. Sorry. Yes. Thank you. Oh, but that's because yes, no, you're right. Okay, perfect. Good. And, well, the same thing in the Euclidean framework. In the Euclidean framework, simply the minus I will be replaced by a minus sign. You see? Okay. So, once you have done that, it's very easy to see that the expansion of this quantity, phi of x1, phi of xn, and well, since one might be a bit confused since I'm both denoting x, those points over which I integrate, and the position of the operator for the green function, let me denote those points z, so that we shall be less confused. So the z's are the position, they are fixed, the position of this. So if you do this, you realize that you can rewrite this functional integral as a functional integral over the field with an action that is the action of the free field times this term times those phi. So you can rewrite this as a sum of a k equals 0 to infinity of something that is nothing but this factor, so minus I over h bar g over factorial 4 to the power k, 1 over factorial of k. Then I get integral over ddx1 up to ddxk of the expectation value of the products of those variables, phi of z1, phi of zn, phi 4 of x1, phi 4 of xk. But this is now integrated with exponential of I over h bar s naught. So this is the expectation value in the free theory. You see. So phi is a free theory, means simply integral over d phi, exponential over I over h bar S0 of phi times the quantity I am interested in, divided by integral d phi, exponential of I over h bar S0 of phi. Okay? So this is the vacuum expectation value of a product of operator evaluated with the vacuum of the theory, omega, while this is another vacuum expectation value of a product of operator, but evaluated on a different vacuum. Remember, this is something like expectation value in the vacuum of the free theory of the time-ordered product of this product of operator. Yes?
In that expression, shouldn't it be the vacuum expectation value times the ratio of the partition functions?
Yeah, I have not finished to write it. This is just the expansion of the numerator. And of course, I have to divide.
Yeah, no, but just consider the expectation value of the free theory multiplied by the partition function.
Of the free theory. Yes, you are right, but this will disappear between the numerator and the denominator. So the numerator gives something like that, time this coefficient, that is the partition function or the exponential of the ground state energy of the free theory, but there will be the same coefficient in the denominator. So at the end, what you get is from k equals 0 to infinity of the same coefficient. Okay, simply the difference here, this is, you have the same integral over the same k points. But now we are computing the vacuum expectation value in the free theory of just the products of those phi 4 of x1, phi 4 of xk. Okay? Good. So that's a very important formula. So this is in the expectation value in the interacting theory. While this is, our expectation value is a much simpler theory, that is a free theory. Okay? So, keep this formula in mind and try to rederive it if you have missed a few steps. That's what's happening between the numerator and the denominator, because you have to understand what it means. But at the end, it's a formula that is not much different from what you did in QFT1. I think you have seen, at least in some simple first order term, this formula in QFT1, that's exactly the same formula. Simply, again, we have derived it by different means, the functional integral, but we get the same results. We are studying the same theory, the same quantum theory. Okay. So, before discussing what the shape, the form of this, one important warning. I made a warning and then I will forget about this problem. In doing this warning, we have interverted two sums. We have interverted a functional integral of the fields times a sum of a k of object like that, you see? And we've wrote it as a sum of a k of a functional integral. So we have interverted two sums, if you want. The sum of a field configuration and the expansion of the exponential into the expansion of the exponential, the series expansion of the exponential, times the integral of a phi. So we have interverted 2, but infinite sums. This is an infinite sum, which is quite reasonable. This is a very, very complicated infinite sum. And in general, interverting sum or series or integrals, when you have infinite sums, this may be very dangerous. If you ask a mathematician and show me, you see, I am doing that. I have this big functional integral over functions, and then I have this expansion I am writing like that. He will say, but do you have a theorem about, I don't know, absolute convergence, which tells you that you can intervert the sum? And you say, no, of course, I have no such theorem, but I don't care. And you will say, well, you must be careful. And in fact, he is right. You have to be careful. Because in this interversion, a lot of things happen, and some of them are connected to physical problems. For instance, the series expansion of the exponential is always convergent. It has an infinite radius of convergence. You see, so this series is always convergent. Once you have performed the intervention and computed the term in this, each term in this, it turns out that these terms may be well defined, but even if you manage to compute it, that's the purpose of renormalization theory, this sum is not convergent. It's not a convergent series. It's only what mathematicians call an asymptotic series. So it's a series in coupling constant that gives good approximation for the exact results when G is small, but nevertheless, it's never a convergent series. So you have to be careful. So the mathematician was right. You have to be careful. But we physicists understand now how to be careful and when to trust this formula and when not to trust it. But keep in mind that there are subtleties. Okay, so now forget about. Keep in mind that you have forget and then put that in one little piece of your brain and continue the calculation. Okay. So, okay, so now once you have done that, well, we are almost done because we can use Wick theorem to compute this products, this expectation value in the free theory of products of fields. It's just a slightly more complicated case than the case that we discussed before of the 2 and the 4-point function. Okay. So we have to come to compute the expectation value in the free theory of products of, how do you have? You have n plus 4k phi operators. Okay? Simply, some of them are at coinciding points. You see? And you have to integrate over the position of those points. You see? So, using this Wick theorem, we end up with the famous Feynman rules and the Feynman diagrammatic representation for the perturbative expansion that I think you have studied already in the QFT1 course. You will get exactly the same rule. Again, we have derived the same rule by different means. Okay? And you have to take the ratio between the numerator and the denominator. So, for instance, well, I think, let us just compute the first term. If you are interested in the phi of Z1, phi of Z2, you see the first term is, you have at the denominator, this will be phi of Z1, phi of Z2 in the free theory, plus minus Ig over factorial 4 h bar times phi of Z1, phi of Z2, phi 4 of x1, and integrated over x1. Okay, plus higher order terms, and divided by the same thing, 1 plus minus Ig over factorial 4 h bar, integral over x1 of phi 4 of x1. Okay? So, this is given by the propagator between between Z1 and Z2. Okay? This is given by minus Ig over factorial 4 h bar. This evaluated, of course, in the free theory. And when you want to apply Wick theorem, you have 2 phi here and phi 4. So, well, let us first evaluate phi 4 of x1. When you apply Wick theorem, this gives you simply 3 times phi squared of x1 squared. Because there are 3 different ways to separate 4 similar elements in pairs of 2. And this can be represented by this diagram. You have 2 propagators at the same point. That's it. So, well, let me first represent the denominator. Here, this denominator is 1 plus minus Ig over factorial 4 h bar 3 times this diagram. Okay, and I represent x1 as a white field vertex, means that implicitly I integrate over the x1. So I can represent this number, the integral over dx of this, by this diagram. Okay? Plus higher order terms. Now, of course, then I am interested, since I will represent an external point like Z1 and Z2 by black field points, just to make the difference. Okay. So here I have a vertex which is like that. So these one are fixed, and this one we integrate over it. Remember? So the rule is integrate over the position of field vertex and external points are fixed because they correspond to some z and those correspond to some x. So now you can do the same thing for this. And here you have different positions. First you can apply the theorem by taking a pair of this phi and then taking the different pairs. So this will give us exactly the same diagram than before. We get this times this diagram. You see? So this represents just the original propagator of the free theory times the integral of these products of fields. Okay? But then we can apply this theorem by associating one phi to one of the phi here, one phi to one of the phi here, and the two remaining phi here. So we get something more interesting, which is, so we have our internal points which carries 4 phi. We have our external these. Of course, here there is a factor of 3. And we can make a pair out of this phi and one of the phi here. I represent this by this propagator. We can make a second pair between phi at point Z2 and one of the phi. And then there remains 2 phi that we can only associate together. So we get something like that. Okay? And then we'll have the next order. Okay. And of course, you have different ways to do this, because we take this one, we can associate it to one of the 4. So we get a factor of 4. Then we take the second one, we can associate it to one of the remaining 3. So we get a factor of 3. And that's it. Okay? Okay. Again, those are numbers. So this represents the propagator, this represents the propagator, this times an integral over all the position of those points of the value of this propagator at coinciding points. This represents a more complicated integral where you have an integral here, a propagator here, a propagator here, a propagator at coinciding points. You take the product of these and you integrate over x. Okay. And then this goes on. Again, it's easy to realize that at first order in coupling constant, this term in the denominator cancels this term in the numerator, but not this one. So you end up with the free propagator between the point 1 and 2. Okay? And then this coefficient, 4 times 3 divided by factorial 4 gives, of course, 1/2. Times these diagrams plus higher order terms. So this is the perturbative expansion of phi of Z1, phi of Z2 in the interacting theory. I'm sorry, perhaps you are not seeing it very well. Okay, so this is the result of the calculation. Just applying Feynman rules. Okay? Good. And we shall discuss more in details what does this number means, how you compute them a bit later, but perhaps next time. What you just need to remember at that time, remember this diagram represents just phi of x in the free theory. And we have seen that this number is infinite. So we are not in a very firm ground. So at the moment, don't worry. We are just discussing the perturbative, the combinatoric and geometrical structure of the terms that are generated by this expansion. We are not looking at the value of those integrals, of those the number given by these. So this will come later. One thing that we can do is we can go back to the theory we started from. You see, remember, we show that in order to define properly the functional integral, we can put the theory on a space-time. So we can replace space-time by a lattice. Well, when you are doing a lattice, you can do exactly the same calculation. Simply, now the fields are defined on point on the lattice. And when you are performing an integral of the point, you are summing of the point of the lattice. But the combinatorics of the perturbative expansion is the same. And if you have a lattice, everything is finite. So we can still consider the interacting theory on a lattice, do the perturbative expansion, then all what I am going to show is valid, and all the integrals and the number are perfectly well finite. And then we take the limit when the mesh of the lattice goes to 0 and see whether this makes sense or not. And that's the purpose of renormalization theory, to see whether this limit makes sense. Okay. So this is, I just show how it works for the two-point function. Let me now just show you on the computer how this works for other green function and higher, and other. So how does this work? Yes, no, my God. What should we like to do? Advanced routing, conferencing. Excuse me, if there is somebody behind the camera.
I've got it.
Yes, can you just activate the video beamer, because I made some mistake in the. Yes, here it comes. Okay. Magic. Yes? Yes?
When you swap things onto a lattice, don't you have to worry about the fact that you're losing all the rest of the...
Of course, but not when just studying the structure of perturbation theory.
So there's nothing that I
So what you have to do is to check whether you recover relativistic invariance in the continuum space-time limit. And the question you ask is a very relevant one, but you should, and you probably have asked yourself this question already for the free field theory. For the free field theory, the propagator on a lattice is not invariant under rotation or Lorentz transformation. And remember, that's the object you studied in the tutorial, the second tutorial. And in this tutorial, I think at the end of the tutorial, you looked at the limit when the mesh of the lattice goes to 0, or if you go to very long 0, and then you recover out of a two-point function that is not invariant under rotation. In the continuum limit, you recover the propagator of the Lorentz invariant or rotationally invariant quantum field theory. So in this case, no problem. You have to break this symmetry in order to define the theory on a lattice, but at the end you recover the symmetry. And there are other ways to modify the theory which do not break Lorentz or rotational invariance. I will speak about them a little bit. So that's another answer to your question. But your question is very relevant. Okay, so now I just give some results of applying the Wick theorem to some of the quantities. So remember, this is the diagram we discussed that appears in the denominator here. This is just in the free theory, the expectation value of a product of 4 fields, x1. Here I have put the factorial 1 over factorial 4, and we have seen that this is given by 1 over 8, the integral over the position of this point of these products of those two propagators at coinciding points, because that's phi of x1 times phi of x1. Okay. Now, if you look at the term that appears at second order, at order g squared in the denominator, so in the partition function of the interacting theory, what you have to compute, of course, is a double integral over 2 points of the products of 2 phi 4. The factor in front of that, there is a 1 over factorial 4 square that comes from each of the interaction terms, and there is a g squared here, and there is a 1 over factorial 2 that comes from the expansion of the exponential at order 2. Okay. So you apply Wick theorem, and you can either make the contraction between the phi here and the phi here completely independently. You get a product of those two amplitudes represented by those two diagrams. If you work out how many terms you have and divide by this term, you get a factor. It's a bit tiny, I think, but it's 1 over 128. Okay, that's what it is. And then, of course, you get other contribution coming from the fact that you may make pairs and compute propagators between some phi here and some phi here. So we get propagator between the point x1 and x2. When doing that, you realize that you can either make 2 pairs between those 2 points. Then you get this diagram where you have a propagator closed on itself, a propagator closed on itself, and 2 propagators between x1 and x2. And you work out the counting factors, you get a factor 1 over 16. And then you can also, of course, make 4 pairs, build 4 propagators between the 2 points. So you get a contribution represented by this Feynman diagram. And the counting factor is 1 over 48. Okay, that's how it works. Now, okay, there is an explanation that I won't have to explain. Well, this is, again, just the calculation that I show you, the diagrams that contributes to the numerator. This one and this one with a factor 1 over, well, this factor turns out to be 1 over 8, exactly like the previous one, and this is factor 1 over 2, so those are the 2 diagrams at the numerator. And if you look a little bit about that, among these diagrams, those 2 diagrams are connected in the sense that you can draw a path on the diagrams going from any point to any other points, while this diagram is disconnected. And in fact, in the combinatorics rule, the reason why at the end you get only the connected diagrams is because the disconnected diagram in the numerator are cancelled by the diagrams in the denominator. Okay? Now, if you go further, the diagrams that comes out in the numerator at second order, so the diagrams that appears here, there are more diagrams because you have to compute expectation value of 2 phi and 2 phi 4. So you have to work more, and what you found, 1, 2, 3, 4, 5, 6, 7 different diagrams. Okay? And you see that among these diagrams there is always a line connecting the point 1 and 2, the external points, but some of these diagrams have disconnected parts. Again, here are the only connected diagram. 3 out of 7. And again, when you take the ratio between the numerator and the denominator, you discover that in the final result for the 2-point function, at order 2 in the complete constant, only the connected diagram are present. Okay. And there is a simple explanation for that I will give later. Now, for the 4-point function, we want to compute the expectation value of product of 4 fields in the interacting theory. For that, we first have to compute the expectation value of a product of 4 fields in the free theory. Those are given by the 3 diagrams that you obtain by applying Wick theorem that I explained before. Then, at first order in the complete constant, you have to compute the expectation value of a product of 4 fields times a phi-4 operator in the interacting theory. And then you get more diagrams. You get diagrams that basically are obtained by replacing a single propagator here by one of the diagrams that appears in the 2-point function at order G. You get diagrams that are obtained by adding those diagrams that appears in the denominator here. And you get a diagram like that, where you have a phi-4 and you pair any of the phi to one of the 4 phi here. You see, you get such a diagram. Okay, and of course these diagrams came out with some combinatoric factor coming from the number of pairings that gives the same contribution. And you see that for these diagrams, the number of the combinatoric factor is 1. Why is it 1? That's because we had a 1 over factorial 4, and we have, when we make the pairing, the first one can be paired to 1 out of 4 possibilities. The second one can be paired out to one of the three remaining factors. This gives a factor 3. The third one can be paired to one of the 2 remaining phi. This gives a factor 2. So we get 4 times 3 times 2, namely factorial 4. So we get factorial 4 divided by factorial 4. That gives 1. So that was, in fact, this is the reason why we choose to normalize the coupling constant term by 1 over factorial 4. Because once you perform the perturbated expansion, you see these diagrams come out with a factor 1, which makes calculation simpler. Okay? So again, among all those diagrams, only one diagram is connected. And it turns out that all the disconnected diagrams cancel between the numerator and the denominator if you compute, well, many, no, I'm sorry. All those diagrams disappear when you compute the ratio between the numerator and the denominator. So those diagrams are the diagrams that appear in the expansion, in the 4-point function in the interacting theory. Okay? So, well, this is the numerator. I wrote again the numerator, but I won't explain that. Here I wrote, so this is the results of the 2-point function. The final 2-point function is given by all this connected diagram. And, well, don't pay attention to this blue box at the moment. This is a 4-point function at order 1. It is given by a sum of these diagrams. These are the diagram at 0 order. These are the diagram at first order. Again, you see that in these diagrams, only this diagram is connected. So the 4-point function involves disconnected diagram. And if you are interested in looking only at the connected diagram that appears in the 4-point function, they will build out something called the connected 4-point function that I will explain tomorrow. Here are, when you go to second order, order 2, here are the connected diagram that appears in the 4-point function. So this is diagram at order 0, free theory, diagram at order G, first order, diagram at order G2. Here you have more complicated diagram, and you see again that you obtain some diagrams by replacing propagator by propagator dressed with this little bubble. These are these diagrams where you had a bubble here onto each of the 4 propagators, but you get new non-trivial diagram where you have 2, 5, 4, and you draw propagators, 2 propagators between the 2, 5, 4. So you get 3 diagrams that are the same topology, but they differ by which external points are attached to one internal vertex. So we get 3 different diagrams. And here are the symmetry factor, 1/2 in each time. Okay? And I think that I will, just for here, again, if you are interested into the 6-point function, then it will be much more complicated. But if you are interested into the connected diagram that appears in the 6-point function, here they are. The first connected diagram that appears in the 6-point function appears at order 2 in the coupling constant. And it is given by this kind of double cross diagram. And you have many other ways to connect those 2 diagrams to those different external points. So in fact, I think there is about 15 or 8, I don't know, 16, or I don't remember. Yeah. Just you make permutation of the external points and you get the different diagram with the same topology. Again, at order 2, at order G3, so now this involves 3, 5, 4. Among the connected diagram, some diagrams are obtained by just adding a bubble to one of those propagators, either on an external propagator or onto the internal propagator. And some diagrams are obtained, in fact, by replacing the cross here by one of the diagrams we got in the 4-point function. And one diagram is new because you get a triangle, and each vertex of the triangle is connected to 2 of the 6 external points. Okay? So you start to see the logic. And, okay, forget about the blue. I will explain what are those blue points, those blue parts of the diagram tomorrow. So let me end with this picture. Yes?
Just to make sure that, so if you compute the correlation function of the interaction theorem.
Could you speak a bit louder?
So just to make sure, if you compute the correlation function of the interaction theory, then you always end up getting a connected diagram.
No. I showed you that you never, in general, you don't get connected graph. For instance, already at the level of the 2-point function, where was it? You see, these are the diagrams that appears in the 4-point function. Already for the free theory, diagrams are not connected.
But you said this connected diagram will be cancelled.
No. What I said is that the disconnected vacuum diagram, the diagrams that are the part of the diagrams that are not connected to any of the external points, they disappear because they disappear between the numerator and the denominator. Okay? But now you may perfectly have diagrams like that are disconnected because already for the free theory, the 4-point function gets a disconnected diagram. What I showed after that were only a subclass of diagrams that are the diagrams that are connected because they are simpler. And in fact, you see already, for instance, that when you have a disconnected diagram, you see you can view it as a product, the contribution of 2 independent connected diagrams of the 2-point function. You see, each propagator is the first term in the 2-point function, and this diagram here is the second term in the 2-point function. So in some sense, when you have a disconnected diagram, it gives a contribution that will be the product of two connected diagrams for a correlation function with less external points. You see? So we are going to discuss this structure tomorrow. Okay?
So, like, only the diagram which has the disconnected internal vertices.
Yeah, something like that. Okay, but we'll discuss that in detail tomorrow. And we'll see how the functional integral methods allows to manipulate this correlation function in a very convenient and global way. Not calculating all the diagrams, but building an object that contains all the diagrams we are interested in. So that's what we are going to do tomorrow. Okay? Thank you.